It's a great honor to be joined today by Dr. Karl Friston. He is a professor of neurology at the University College London and one of the world's most influential neuroscientists. He invented statistical parametric mapping, voxel-based morphometry, and dynamic causal modeling, all of which are statistical techniques foundational for modern neuroimaging, such as fMRI, involved in my own research and those of countless others. Dr. Friston has authored or co-authored hundreds of scientific publications detailing out these theoretical and methodological advancements in neuroscience. He's also the mind behind the theory of active inference, the free energy principle in mind, brain, and behavior, detailing out a theory of consciousness that you've called physics of belief. Dr. Friston, welcome to the Nature and Nurture podcast.
Thank you very much for inviting me, and thank you also for that lovely introduction.
You've spoken of the brain as a fantastic organ. Fantastic not only in the sense of being amazingly complex, but fantastic that it's constantly generating fantasies.
That's absolutely right. And that speaks, I think, to a long-standing sort of appreciation of the brain as a constructive organ, constructing hypotheses, explanations, fantasies that best explain the sensorium. So, that's one of my favorite ideas, which I guess you can trace back to Kant, but certainly very nicely articulated by people like Helmholtz in the 19th century. And to my eye, resurgent in the sense that things like predictive processing have become a really dominant paradigm in cognitive neuroscience. And I would imagine some of your fMRI studies, the notion that the brain is actively there as a statistical organ constructing fantasies that best explain what we see and what we hear and what we feel.
Absolutely. And I'm a developmentalist, so I study adolescent brain development, which I'm hoping we can get into later once we lay out the groundwork for the active inference theory. Now, I know that your early career began in psychiatry, and you did a lot of research on schizophrenia, which you could call mental illness of the brain being too fantastical. Does this connect to what later became the groundwork for active inference?
Yeah, in a very deep and pragmatic way. I mean, much of the theoretical neurobiology that you refer to, things like the free energy principle and active inference, that came from an approach to understanding psychiatric disorders as a kind of false inference. So, the idea here was, if psychology is all about predictive processing, active inference, sense making under uncertainty, then psychopathology must then be a reflection of some kind of false inference, of the kind that, as a statistician, you would know as type 1 errors or type 2 errors, inferring things are not there when they are, as in neglect syndromes, or inferring something is there when it's not, such as in hallucinations and delusions. So, that foundational training, clinical training, really set the direction of travel in terms of the theoretical developments. Interestingly, in your introduction, en route in that direction of travel was the application of the machinery of sense making to imaging time series data. So using exactly the same techniques that we are now supposing is a metaphor, or indeed a description of the way that the brain makes sense of sensory time series or sensory streams. We were using exactly the same mathematics and modeling approaches to make sense of fMRI time series and brain imaging time series. But all that started with schizophrenia research, absolutely.
Is this because what the brain is doing when it's making predictions is it's all fundamentally probabilistic, because the world is constantly changing in front of you and there's uncertainty involved?
Yeah, I think that's a very nice way of expressing it. Sometimes cast in terms of making decisions, whether they're perceptual or sort of choice behavior-like decisions, they're always under uncertainty. So as soon as you mention uncertainty, you are implicitly committing to a probabilistic description of either those decisions or the way that we try to explain our sensations. But I'd probably go a bit further than that. I mean, if you look at all of physics, it's all about uncertainty and measurement. I mean, quantum physics just is a theory of probability distributions. And if you see those probability distributions being updated, or you put measurement into the mix, you basically have a statement that physics is inference. And I think that theme follows through in terms of the mechanics behind statistical thermodynamics, for example. It's all about distributions, and indeed most of the things that we measure can, such as temperature, just depend upon probability distributions. And from the point of view of active inference, our inference about those probability distributions.
There's a very elegant pairing of something objective and physical, like entropy, with something that we normally think of as subjective and perhaps not able to be quantified, like belief. But then what this active inference theory is doing is that when we're making predictions, there's going to be a certain degree of error in our predictions and our beliefs. And you can quantify that with entropy, right? And what the brain is trying to do is minimize that entropy or uncertainty or free energy. Are these all interchangeable terms here?
Yes, I think that's absolutely right. And again, well expressed. Let me sort of slightly nuance it, because there are different perspectives on these different descriptions of probability distributions. So the free energy principle as an account of self-organization is an explanation for why certain kinds of systems avoid the natural tendency to disorder and dissipation. So often articulated in terms of the second law of thermodynamics, that there's a progressive increase in the entropy of closed systems. So why is it the case that things like you and me do not progressively become more dissipated? Why don't we just dissolve into the environment? Why don't we evaporate? Why don't we decay? And therefore one has to explain, or at least describe, things like you and me in terms of resisting that entropic decay. But the entropy in this instance is basically the entropy of our sensed and physical states. And the way that you get to that is by basically trying to minimize the surprise that you would engender by sampling the world in a particular way. Technically, that surprise is known as self-information, and the average of a self-information or surprisal is known as entropy. So you can get from an explanation as to why the entropy of our sensed world is upper bounded by expressing that as succumbing to or committing to the imperative to minimize self-information or surprise. And that surprise is bound or approximated by the free energy. So at that level, all of those things are synonymous, but there's an interesting, if you like, twist or nuance. When in doing that, we also have to estimate the uncertainty of our predictions that are necessary to evaluate the surprise, sometimes described in terms of prediction error. And that is a really important aspect of the kind of belief updating that active inference covers. And I mention that specifically because it ties into the schizophrenia issue, that if we are unable to estimate the uncertainty of our beliefs or the confidence that we should be ascribing to any sensory information, then we are very subject to drawing false conclusions. So we come back to the delicate game of getting the best explanations for our sensory input. And that game is rendered very, very delicate because of the difficulty in estimating the degree of uncertainty we have. So I think from the point of view of a clinical neuroscientist or indeed a psychiatrist, then that special aspect of uncertainty quantification, representing our confidence or uncertainty in our various beliefs, whether they're subpersonal beliefs or propositional beliefs, is center stage in understanding the ways in which we can succumb to false inference.
This anti-entropic process of consuming outside energy to maintain one's form and avoid decay is a useful definition for what life itself is or is doing.
Yeah. And one could regard the free energy principle as really addressing that issue, usually framed though in terms of what properties must a system possess in order to exist in that sort of entropy defying sense. So the physics part of the free energy principle really starts exactly from that observation that there are certain things that tend to resist this tendency to increase in their entropy. And then you ask, well, what aspect of their dynamics can account for this apparent resistance to being dispersed by random fluctuations or perturbations from the outside world? And the answer ends up being simply that you've got to counter the dispersive aspects of all these perturbations and fluctuations with a systematic gathering yourself together around those states of being that you are characteristic of you, that define you in some unique sense.
You speak in your book about two separate roads to active inference. The first high road, I believe, is what you were just discussing, where you begin with this free energy principle. And if the goal is to minimize entropy, then any anti-entropic system will eventually arrive at active inference of a process of making that happen. And then the opposite, the low road to that, would be assuming you have an agent who's modeling the world and making predictions and having some degree of error there and aiming to minimize error. That would be more of a bottom-up approach. Is that right?
Yes, you've taken my favorite sort of dual approach to it, absolutely. And I very naughtily started with the high road. I'm sorry for that. Yeah, you're absolutely right. But I think that it's useful you introduce that distinction. From the point of view of a physicist, we're just talking about something which is unremarkable and not has no anthropomorphic story. It's just that should certain systems have technically what is called a pullback attractor, should they sort of converge to a certain set of states that defines the kind of thing that they are, then they will be equipped with a description that can be unpacked, a story, if you like, that can be unpacked from the point of view of the low road, which is what would these systems look like? Well, they would look like they were trying to minimize their surprise, where they would look like their internal dynamics, whereas the neuronal dynamics was in the game of minimizing prediction error. And then you get the low road story, which brings us back to this long pedigree or legacy, or from Plato via Kant to Helmholtz and all the intervening theorists, people like Richard Gregory, perceptions hypothesis testing, the idea that, again, that the brain is a fantastic organ, that it is actively trying to minimize its prediction error. And then you get into the 21st century with predictive processing being the way that people generally think about neural dynamics as trying to minimize precision-weighted prediction error. I slip in there precision-weighted because that was a nuance I was talking about before. It's not just a question of minimizing prediction error as a way of understanding this existential imperative to minimize surprise. But you have to also do it in proportion to the precision that you afford certain prediction errors. So the precision is the inverse uncertainty. So that's what I was saying, trying to imply before, that not only are we overall anti-entropic machines, but in reading that the dynamics that render us resistant to entropic forces, we can be read as, or it looks as if we are actually estimating the uncertainty about our own inferences and our own predictions that are, I repeat, necessary to elaborate a prediction error or to quantify the surprise in this moment, and how we're going to use that surprise or prediction error to update, revise our beliefs about states of affairs out there, and indeed what we're going to do next.
This is a great place to bring in the hierarchical processing element of active inference, because it sounds like when you're talking about precision there, if we think about ordinary human consciousness, there's a whole bunch of things that are going on that you're not really aware of. Like we lack the precision to detect, the dust motes that are floating around in the air, but perhaps if you were a small fly or like a microbe or something, as long as there was still some motivation or some degree of predictive processing at all, then suddenly those tiny details become a lot more relevant. So that's an example of precision, yes?
Yeah, no, absolutely. Yeah. So there are two themes you've introduced, both of which I'm tempted to pursue. One which is exactly the sort of the precision and the coarse graining that we necessarily bring to our explorations and to our fantasies, and we all have the right degree of coarse graining. And certainly, if I was a fly, I would be operating at a much smaller scale and wouldn't sort of coarse grain to the same extent that you and I would, being much larger creatures. So there's a really interesting and very, very important theoretical explanation why there is an optimal degree of coarse graining. The other issue you brought, the other sort of architectural issue about sense making and coarse graining, is the hierarchical aspect. So you can actually think of successive levels of, say, the cortical hierarchy in our brains as doing a special kind of coarse graining as you get deeper and deeper into, or higher and higher, ascending these hierarchies. And that kind of coarse graining is usually not just over sort of, say, space in the sense of receptive fields in vision, but crucially also over time, that we're sort of lumping together epochs of time at successively longer time scales in the way that we generate those fantasies. So I don't know how much you want me to unpack that. Which direction would you like me to go? The imperative to coarse grain in the right kind of way, or the importance of hierarchical processing?
Here might be an idea that connects them together. So are the systems of the agent, which is doing the processing themselves, are those something that are flexible and could be redefined? Because most of the time when we're talking about consciousness, we're talking about the whole human, but you could also, from the perspective of an individual neuron, have its predictive processing in response to its immediate chemical environment, and that would be on a much smaller both time scale and physical space scale. So that seems to be one of these trade-offs of precision, where like the smaller the agent in question is, or the system in question is, the more precise you get. But then these larger systems can be assembled from collections of smaller subsystems, as in the case of the brain, and millions of neurons, billions of neurons interacting.
Yeah, well, so that does certainly link the two themes and brings a very important principle to the fore, which is the scale invariant principles that could be applied, as you say, to a single neuron, or indeed even probably at the molecular level. So what is conserved over different scales, be they sort of at the neuronal level, at the mesoscopic scale of a neural population, or a macroscopic scale that you might apply to, say, intrinsic brain networks that have this hierarchical kind of structure. The principles are exactly the same, but the scale at which they are operating is clearly unique to the scale that you want to identify. And I think the important insight here is that for these principles to operate, these predictive processing, free energy minimizing principles to be in play at any given scale, they have to be afforded the right context by exactly the same processes at the scale above. So, for example, for my favorite hippocampal cell to operate properly, it has to be in a milieu and have the right connectivity with the hippocampus as an organ or a system. And for the hippocampus to exist, it has to be living in a brain, and for the brain to exist, it has to be living in a body, and the body has to live, right out to the biosphere. So at every scale, you have this this nesting where the scale above provides the right kind of context for the scale below to do its sense making, its surprise minimization, its self-evidencing, and yet at the same time, that lower level scale is now coupled to and informing and creating the context in which these processes are going on. So that's a really important sort of generic observation about any kind of self-organization, and really starts to bite when you start to think about, say, psychological or neurodevelopment in an evolutionary context, or indeed an evo-devo context. The same principles are operating at an evolutionary, very, very slow time scale that are coupled in both directions to faster time scales, say, for example, developmental time scales, either of the kind in very early neurodevelopment that we determined epigenetically, or during the lifetime, that themselves contextualize experience-dependent learning as it unfolds over hours and days and weeks, as in procedural learning, that itself contextualizes short-term sensory learning, that itself then contextualizes the inference in the moment, sense-making, perceptual synthesis. And of course, all of that chain of moving down the scales can now be rehearsed by moving up. That I need to do the right kind of inference in order to have the right experiences, to get the right kind of experience-dependent plasticity, to do the right kind of learning, which enables the right kind of structure learning, that enables the right kind of adaptive fitness of my phenotype, that enables me to, or my phenotype to be represented in the next generation. So that observation, that scale-free aspect, and the intimate coupling between different scales, I think, is something, a fundamental observation about, well, certainly biotic self-organization, and possibly all kinds of self-organization, that transcends neuroscience, but certainly hits you in the face when you start to think about the different kinds of neuroscience you might want to do or pursue in your career.
If you began only with the low road version of the story, which seems to take as a first principle the fact that you have some system that's engaging in prediction and error correction, you might be faced with the criticism of, how do you know this isn't just an elegant heuristic model of what's going on as opposed to what's actually going on? But it sounds like as soon as you combine it with these high road properties of scale invariance and free energy minimization, then you have a stronger case that this is actually what's going on.
Yes, I've never heard that expressed like that before. I think that's absolutely right. Yeah. There is a danger, though, but that once you endorse or provide a complementary perspective on the low road predictive processing story with a high church physics of self-organization in to non-equilibrium steady state, that you can almost trivialize the problem, because the physics, the high road explanation is very deflationary in the sense that all it's saying is that systems that have characteristic states behave as if they are attracted to those characteristic states. So it's almost tautological. And so, in, if you like, providing a construct validity or an explanation for the low-road predictive processing story or predictive coding story, if you're talking about precision-weighted prediction errors, you're also treading in the dangerous waters of providing a tautological, almost tautological account of what's going on that could potentially explain everything in a very weak way. But I concur with your observation that the fact you've got this deflationary story, it could be no other way. And it just looks as if we are carefully constructing in a purposeful way good generative models, good fantasies that explain our sense to world. It is actually very compelling, and it sort of begs the question, is it just that this is our way of understanding ourselves, or is there a deeper question or a deeper explanation for why this has to be the way that we operate, and it could be no other way?
Active inference to me seems to describe a computational process of cognition, but doesn't necessarily describe what it is that's doing the computation. And I'm wondering how this connects to integrated information theory, which is another theory of consciousness that essentially argues that all matter carries a certain degree of information, even at the basic physical level. And then as it begins to interact, you get shared information across coupled systems. And as those systems grow more and more complex, they contain more and more information. And at a certain point, you get a system which can reference itself. And that is how consciousness is defined. And I think if you begin with that definition of what a conscious system looks like, and then apply active inference to it, the whole thing seems to fit together very nicely in my view. But I usually see these as competing theories as opposed to complementaries. I'd like to hear your thoughts on how they fit together or don't.
Right. Well, I'm very happy to share my thoughts. I'm smiling because I am currently involved in a Templeton Foundation adversarial research collaboration to pitch IIT against active inference and predictive processing. So that presupposes that one or the other is right. And I'm smiling because I agree with you. I think they're entirely compatible. But I can't say that in public because the adversarial research collaboration to show that one is a better explanation for empirical evidence than the other. But I think you're absolutely right. I mean, the free energy principle and IIT are very different things. But in their difference, it means that there is, I think, a very clear way of them shaking each other's hands. First of all, the free energy principle is not a theory of consciousness. It's a theory of self-organization that ultimately inherits from the physics of things that persist that can then be read as a physics of sense-making or sentient behavior. But sentient is just a description of the kind of behavior that these systems evince. It's a first principles account. It's literally a variational principle of least action. It can also be cast as a constrained maximum entropy principle. It's an example of the principle of unitarity in quantum information theory and quantum physics. And I could go on. So it is a first principle account that is predicated on or starts with the natural laws of physics. So it sort of comes along with a naturalization baked into it. IIT is an axiomatic theory. It is based upon 5 axioms. I think it's 5 axioms that make some claims about or assumptions about the nature of consciousness, and sort of then works backwards to see what kind of information theoretic treatment would accommodate or be consistent with these axiomatic claims. So in virtue of the fact that these two approaches start from very, very different ends, one with nothing to say about consciousness, and the other one starting from an axiomatic specification of what it is to be conscious, or what it is a conscious system must possess. I think it's perfectly possible for them to meet in the middle. And all the tenets of integrated information theory, I would be extremely surprised if you couldn't find all of those predictions and tenets in particularly a hierarchical message passing scheme, where the message passing scheme was prescribed by an application of the free energy principle.
IIT is sometimes criticized for being panpsychist in the sense that if it defines consciousness as information and any matter can carry information, then it says everything is conscious to some degree, even if your keyboard is only a little bit conscious and life is much more conscious. And active inference we talked about as part of this anti-entropic process, which is also the same process that life works by, where again, it's consuming excess energy outside the system to maintain its own form. Does active inference say anything about whether this type of predictive processing either requires the system to be alive, or maybe the other way around, where if it's alive, by definition, it is engaging in predictive processing?
I think, again, that's a great question. I mean, it would certainly say to be alive is to have, to be describable as being engaged in predictive processing. And that, can be expressed in many different flavors. Jacob Howie and his colleagues like to describe this as self-evidencing. So mathematically, surprise with self-information is a negative log of something called model evidence, the evidence for your fantastic model, your internal model, your generative model, your world model. So as you minimize the surprise or variation of free energy, you are also equivalently maximizing the evidence for your models, hence your self-evidencing. So that means to exist is to self-evidence, and that just basically means it will look as if things that exist, or certain things that exist, will look as if they are behaving to garner evidence for their models of their lived world. But notice I said certain things, because that comes back to now a difference between the free energy principle and IIT, and you've drilled down exactly on that key difference, which is this notion of panpsychism. So from the free energy point of view, and certainly active inference point of view, it would, you would have to specify what you mean by a certain kind of thing that can be conscious. And I think the answer to that was very much buried in the way that you phrased your question. You were talking about maintenance and self-reference and the like. All of these things are active processes. So at some point, you have to write into active inference what you mean by something possessing a sentience or a consciousness. And what normally transpires is that there has to be an active aspect of it, an auto-poetic aspect. There has to be some notion of self-assembly. There has to be some certainly notion of self-reference, but in a way that actively, to use your description before about sort of doing work, expending energy to minimize the entropy in a thermodynamic sense. That then tells you that you really have to commit to a particular kind of have to commit to a specification of what you mean by sentient behavior and consciousness in relation to action. And that is not something that IIT has. It's not about things that act upon other things. It's just about the statistical dependencies of systems that would be necessarily possessed by something that is conscious, but it doesn't tell you whether it is conscious because it possesses this particular kind of statistical dependencies. Active inference, on the other hand, gives you an opportunity to say, well, there are different kinds of sense making, there are different kinds of self-organization, and some of them may be equipped with the features that that would underwrite sentient behavior. And then you have to ask, well, what are they? And normally the story goes, that you really your fantasies, your generative models, your internal models have to entail the consequences of your action. So now you become an agent. So there are lots of things to which the free energy principle applies. Not all of them are agents, but there is a certain special kind of system defined technically in terms of the coupling between various states that constitute the system and its environment that could be ascribed the quality of agency, and that entails a degree of planning, that itself entails a degree of future modeling, it entails a degree of selecting among counterfactual futures. So for these kinds of systems, then you would certainly, well, there are people who would certainly say that you have to have this as a minimum and necessary set of properties in order to qualify as potentially being conscious. So notice there can't be panpsychism under that argument, whereas there can be under IIT. So there is a bright line, I think, when it gets to that level of argument. But it does depend very sensitively on what you would consider to be conscious.
So if existence itself is self-referencing, and at the quantum level, particles are fundamentally probabilistic, which seems to be a form of activeness, and they can become entangled, which seems to have some degree of future prediction. Why doesn't that become panpsychist in the sense that any single particle could be an agent?
Right, because just being entangled and just existing does not qualify you as an agent. So to put it very simply, if you can plan, if your internal dynamics represent the consequences of your action upon the world, then you can be called an agent. If you can't, then you can't be called an agent. So a particle can't plan, the weather can't plan, your thermostat can't plan. All of these things are certainly subject to, or one can apply the free energy principle to all of these kinds of things. Evolution can't plan, you can apply the free energy principle to evolution. Natural selection becomes Bayesian model selection. But none of these things, 8 of these scales plan. So that's what I was trying to intimate before about the importance of being an agent and the importance of having a special kind of generative model that arises from a particular sparse coupling between the inside and the outside, and in particular, the ability or the availability of our active states, or the way that we act upon our world, to the internal sense-making dynamics. And paradoxically, if you disconnect the active states from, say, the neuronal states, so that now you are not in direct receipt of the states of, say, your autonomic reflexes or your actuators, your striatal muscle, for example, but you can only sense the consequences of your motor acts or autonomic acts, as is the case of things like you and me, then your actions now become hidden from you, your sense making and your fantasies, and you now have to infer your own actions. And that becomes, one way of articulating that is that action now is the consequence of planning as inference. And so unlike most systems where the active states that constitute a separation between the internal states and the external states are directly influencing the intracellular states, there are a certain special kind of systems where their own actions now becomes a hidden cause of their sensorium. And it is I think, the unique province of these kinds of systems that would qualify for the kind of self-maintenance and self-reference that you're talking about. So I'm not using, I wasn't reading self-reference here as some, say, recurrent dynamic. I'm reading in a very literal sense that I have to refer to my own sensations to infer the consequences of my own actions. but I don't have direct access to them. And as such, then you become a special kind of particle, and potentially the kind of particle that could be conscious. And implicit in that construction is the kind of particle that could be equipped with the label agency. You can also argue, because the consequences of one's own action, when inferred and indeed when planned, are in the future, then you have to have a fantasy or a generative model that has a certain temporal depth to it. So you're now transcending the present moment. So the way that we make sense of our world, unlike a thermostat, is in terms of narratives that run deep into the future. And it is that sort of, if you like, special aspect which eludes panpsychism. So these kinds of systems are pretty rare. And you may argue that they are definitive, certainly they are definitive of beyond just biotic self-organization. So you could have an interesting argument about whether plants plan. There is actually some evidence that they can actually plan. I've enjoyed writing with colleagues in plant biology, but I certainly know that thermostats don't plan. So a thermostat is a really nice example of a sort of a system that controls its own environment. It is anti-entropic in the sense that it keeps the temperature within bounds. It does all the right things you might want of any machine that is sort of self-referential in a very simplistic sense, but it doesn't have the kind of self-referential aspect that I was speaking about, that is entailed by the capacity to plan and select from various plans and infer what is the most likely thing I would do given the sensory evidence at hand at the moment, under the belief that I am actually the agent and the cause of that sensory evidence. And it is that aspect of inference that I think draws a bright line between an agent and an artifact with autonomy. And I would argue that consciousness and certainly sentient behavior really belongs to agents and not just systems that have autonomy.
Would you say then that the error that is measured when engaging in active inference is not just what is going on in the actual world versus what is the system predicting? Because that could seem to apply to a thermostat. You can measure the degree of uncertainty in the thermostat rating, even though it has no vested stake in the outcome of that rating, versus if it's a true agent, then it's not only error between actual world, but predicted world and something like desired end goal.
Yes, yeah, absolutely. And that can be expressed very simply at a number of levels. You could actually just write it down in terms of prediction errors. So it's not just the prediction error between my predictions and my sensory data, but it's also the prediction error between my beliefs having seen the data and my prior beliefs before seeing the data. And those prior beliefs define the characteristic states that you would expect yourself to be in. So these would be, for example, sort of very subpersonal and possibly epigenetically specified innate priors that underwrite the set points of our homeostasis. So the fact that I have a particular characteristic bodily temperature is an expression that my brain, to the extent it controls my body temperature, has this prior belief that's the kind of thermoreceptive information I would expect to receive. And of course, I can get hot and cold, and I sense the hot and coldness by minimizing the prediction error between my thermoreceptive input and my subpersonal beliefs about the current temperature. But in moving away from my prior beliefs, I also induce another kind of prediction error, which is the disparity between my posterior and my prior beliefs, and that I'm going to try and keep as small as possible. So the prior beliefs you bring to the table as a phenotype have a fundamental role in essentially making it look as if you have some sort of purpose, simply because they a priori describe the kind of states that characterize you as this kind of thing. So mathematically, it's called a pullback attractor or an attracting set that but you have to occupy, set of states you have to occupy to be you. And if you wander away too far, then into very uncharacteristic, surprising states, you cease to be what you are. So I'd be a very, very hot me, probably a dead me if I had a temperature of 112. So priors, I think, are absolutely important. They become even more interesting when you think about how do I choose actions, make decisions, life choices. And these can be at any different scale. So at the a very fine time scale of the cognitive moment, or perhaps the perceptual moment, these would be, where do I choose to look next? I have to make that decision every 250 milliseconds as I stochastically palpate my visual scene to secure the right kind of visual input, through to choosing, do I do a PhD or not? Or, do I go for a postdoc or go into, continue my clinical studies or whatever? All of these are instances of subpersonal and possibly personal decisions that involve rolling out into the future and asking, in your fantasy, in your generative model, what would happen if I did that? And then you score it in terms of effectively like prediction errors, but these are prediction errors about things that haven't yet happened. So they're technically they're posterior predictive densities. And what transpires is that if you just go back to the physics of self-organizing systems and work out the most probable actions that these systems take, they actually comply exactly with the two aspects of Bayes optimality. One aspect is what we were just talking about, which is effectively acting in a way to minimize the prediction error or the divergence between what a priori I expect something like me to encounter and what would happen if I did that. And therefore, I am more likely to choose those courses of action that bring me towards what I a priori expect to hear. We sometimes call these prior preferences. And these define the kind of outcomes that I would expect to encounter. But just out of interest, there's another very important component to technically what's called an expected free energy, above and beyond that expected value, where value is just the log of my prior preferences. And that's expected information gain. So once you start to apply these this mechanics to things in the future that are consequent upon action, you now have another kind of Bayes optimality, which is the that comes from the Bayesian principles of optimal experimental design. And what that just says is I act in a way that resolves the greatest uncertainty and identifies the best fantasy that is most precisely specified because I've got the right kind of information. And it's that expected information gain that drives eye movements. So we don't look here or over there in order to get reward or to satisfy some utility function. We do it because looking over there means that I'm going to resolve the most uncertainty about what caused those peripheral visual sensations. In other words, looking over there, making that choice has the greatest expected information gain. So that's a really important aspect of creatures or systems that can plan or engage or look as if they're doing planning as inference, that they are quintessentially curious, or they will look as if they're curious. So that would be another thing, if you like, that draws a bright line between an active inference formulation of sentient behavior and more descriptive information theoretic descriptions of what it would be necessary, what it would look like if you could measure something that was sentient. That you have a description of sentient behavior that is at its heart has to be or evince some kind of curiosity, responding to epistemic affordances and salient, purely to look as if it is sating itself with the intrinsic motivational value of finding out what would happen if I did that, or what's behind that door, or what does this person think, or what kind of person am I? Can I move this? Is this my arm or is it yours? All of these questions have to be actively resolved by sampling the right kind of information, the right kind of sensory evidence, which means that you have to choose the right actions and decisions in order to answer those questions. So I would say that was one hallmark of conscious behavior. Very simply, curiosity, that's an integral part of planning and agency.
Right, this prior motivation for maximizing information gain seems to get at a fundamental paradox of free energy minimization, because if you were purely after minimizing entropy, you would think that you would engage in the most narrow existence possible, just pure repetition, where nothing new ever happens, but at the same time, error is relatively low.
Yep, no, absolutely. This is the dark room problem, isn't it? That's when so that the dark room paradox was introduced exactly to sort of challenge the free energy principle formulation that, if I really want to minimize my surprise, I just go to a dark room, switch off the lights, lie down and close my eyes. And I often think cheekily, well, yes, I do that every night. But aside from that response, I think you've exactly highlighted it. It is because we are curious creatures. The first thing that we will do, in fact, we would have to do in order to survive in the long term, when entering a dark room, is to switch on the light, because this then maximizes the expected information gain. It resolves any ambiguity about my sort of low illuminance visual input. So just out of interest for your amusement, the formulation in terms of expected information gain and the full elaboration of the free energy principle to accommodate this expected free energy conditioned upon plans as we project into the future actually came as a response to critiques based upon the dark room problem. So this is a nice example of sort of adversarial theoretical debate, actually pushing the free energy principle to a more formal and principled stance, so that it could exactly address that that particular pushback.
Where does free will come into viewing our minds as just aiming to mathematically optimize for lowest uncertainty and highest expected information gain?
I think that's easy to answer because the answer is again predicated on the notion of entertaining counterfactual plans that roll out into the future. So as soon as you have a set of plausible courses of action, amongst which, and you have to infer the consequences of this plausible set of behaviors, you now are in the game of having to select one amongst a set of plausible courses of action. And I think just having the verb select as part of active inference immediately touches upon the notions of free will. There is always going to be, in any Hanninger's inference, something that can be read as an act of Bayesian model selection. And it's you doing that selection, no one else. And no one else could even see you doing that selection because you're hidden behind your sensory veil, your Markov blanket. So only you know what you're selecting from. It's your plans and you're selecting from it. So I think free will, sort of, certainly one minimal and rather simplistic reading of free will, is an emergent property of this kind of creature that can engage in in this kind of planning. And I love this notion of Bayesian model selection because it just speaks to sort of free selection in sort of quantum physics, for example, free will in philosophy, natural selection at the evolutionary timescale. I'm not saying that natural selection exerts free will, but it certainly has the same job of selecting the phenotypes with the lowest free energy or the highest adaptive fitness or highest marginal likelihood or model evidence. But because we're actually doing this in our heads in the future, I think that would that has, I think, all the necessary properties that you would be that you'd need, I think, to convince somebody that this thing does actually have free will.
Indeed, we're getting more into philosophy than neuroscience here, but do you think there's a meaningful difference between we actually making those decisions versus something like the brain is doing this automatically and the experience of these decisions is epiphenomenal?
That's a very good question. I think, well, as I say, it's probably not so important what I think, but certainly in people or in discussions with people, which are actually ongoing at the moment, and literally, I'm involved in have just recently been involved in a Lorentz workshop addressing phenomenology and asking exactly these kinds of questions. I've just been revising last night a paper trying to address this and look at the sort of the minimal assumptions you need to be you need to bear down this. But I think that the answer to the question that's emerging from these discussions is yes. It is epiphenomenal in the sense that the kind of actions that we are talking about that enable the right kind of sense making and planning are not in themselves experienced, but we experience the consequences of those mental actions, as it were. And if that is the case, then you could certainly say that in recognizing the fact that I am attending to this, or that I have just looked over there, it is an epiphenomena. But there's a twist to that. That epiphenomena actually will cause the next change in attentional set and the next action. So it's both, the epiphenomena is both cause and consequence, just in virtue of this hierarchical structure that we were talking about before, that is a necessary property of most generative models of most sophisticated life forms. That no one, if you like, personal or subpersonal belief, and now we're talking about some things that are clearly propositional, qualitatively, that would be experienced. No one neuronal representation or encoding or parameterization of these belief structures is epiphenomenal in the sense that it is both cause and consequence of other belief structures in the brain. So I think, yes, you're absolutely right. Our sense of self, for example, our all valenced senses of states of being, of an emotional state. I'm in pain, I'm tired, I'm in love, I'm embarrassed, to various degrees. All of these are fantasies we bring to the table to best explain the myriad of interoceptive, exteroceptive, proprioceptive inputs that constitute the evidence for, yes, I'm in this particular state of anxiety or fear or pain. So on that level, those experiences are epiphenomenal in that they are caused by the sensations. But remember, because you have to control the precision of your prediction errors in order to select the right sensory evidence and to attend to the right sensory evidence, all of those epiphenomenal representations are actually the cause of the way that you actively sample in a planned way those particular sensations. So I think we are getting very philosophical now, but also I think into realms which are practically very important in terms of the neurobiology of interoception and selfhood, and the pathologies that can attend various abnormal inferences or false inferences or failed inferences about selfhood, and understanding the mechanics of this kind of belief updating entailed by the neurodynamics, I think is actually quite important. But in answer to your question, yes, they are epiphenomenal in relation to the actual acts or attentional deployments that we prosecute, but we can always sense the consequences of those.
It makes sense from an evolutionary perspective that we would evolve to experience lower than average or lower than expected uncertainty as positive and higher than average or higher than expected uncertainty as negative. But at the neurobiological level, how is the uncertainty actually translated into affect?
Well, I think the answer to that question is almost identical to sort of the general answer I gave you before. I think notions like "I am anxious" is just a hypothesis. It's a hypothesis that best explains the fact that I got a mild tachycardia, that I have a certain sort of proprioceptive pattern of inputs that suggest I'm either in a fright or flight. I've got, say, increased muscle tension. It's a hypothesis that is fully endorsed by the fact that I can't see who's around this dark corner in this dark alley. All of this, situated sense making is best explained by the simple hypothesis, I am anxious. And of course, this circular causality I was referring to, well, because I am anxious means that I will expect to have a certain set of tension in my muscles. I will expect to have a particular tachycardia. I expect to have a certain degree of perspiration up or down. And those predictions are now fulfilled by active inference. So I now cause my bodily states that are providing evidence for the hypothesis that I am anxious. And it's interesting that you sort of draw the you play the evolution card. I don't think you even need to play the evolution card in saying that being anxious has negative valence. Remember that the whole point of the free energy principle, the whole point of existence, is to minimize self-information or expected free energy or expected surprise. That just is uncertainty. So that is entropy. Entropy is the average or the expected surprise or self-information, expected prediction error. So existing, which we assume is the realization of our pullback attractor, our attracting set, is, if you like, like a temperature. It is the measure of goodness, and we've just realized that in terms of making sense of our own sense making. So I think it's a really useful observation that nearly everything that is negatively valenced in terms of these various hypotheses about states of mind that I could entertain with a greater or lesser coarse graining. I could be alexithymic, or I could have a very fine-grained understanding of my emotional states, that are nicely nuanced, so I'm not just left with I feel good and bad. But certainly the axis of good and bad is always tied to a degree of uncertainty, whether you're talking about sort of depressive disorders, or their maintenance, or obsessional compulsive disorders, or literally anxiety disorders, generalized anxiety disorders. They can all be, if you like, easily understood with the simple mnemonic. If it increases uncertainty, it's going to make you feel bad, or commit to the hypothesis, I feel bad in some way. I experience some kind of angst that has a negatively valenced aspect to it. But you see this everywhere. You see this in the economic markets. What's the bad thing? It's not to do with being poor. It's just uncertainty. It's just uncertainty in the market. The markets have lost confidence. That's the only thing that makes a bad market. You see it in homeostasis. What's bad from a homeostatic point of view? It's just not knowing, well, from the perspective of allostasis, whether my homeostasis is going to work. So nearly everything we do, certainly as prescribed by the free energy principle, is just about making the world more predictable and more certain and less uncertain. And any failures to do that, or any excursions from that trajectory, will be experienced as naturally experienced as alarming or negatively valenced.
And these hypotheses needn't be conscious, but they could be referring to autonomic nervous system behavior.
Oh yeah, I would absolutely. I mean, I think sort of being able to articulate propositionally or in conversation, and to have the phenomenal experience of having these emotions. I think they have to be personal, but the mechanism upon which they rest and the systems that they control in terms of instantiating various attentional sets or setting the synaptic gain in the right kind of way in your anterior insula, right down to the periaqueductal gray. And if I was Mark Soames, I'd say that the heart of feeling is just in the executive of setting the neuromodulatory tone at the level of the brainstem. So he refers to this as felt uncertainty. He thinks that all consciousness certainly has to have a rite of passage through the brainstem that is basically the biophysical encoding of the uncertainty or precision, the inverse uncertainty, which is the precision we were talking about before, that is then broadcast to the rest of the brain. But that would be, sorry.
Is that neurochemical signaling analogous to modifying numerical weights in like a black box of an artificial neural network?
Yeah, no, it's exactly the same. So, I mean, from the point of view of neurobiology, it's just the particular example I had in mind then when referring to felt uncertainty in as talked about by Mark Soames, were the cells of origin of the classical modulatory neurotransmitter systems, dopamine and epinephrine, serotonin, and the like. More generally, it would include any synaptic mechanism that changes excitation inhibition balance or postsynaptic excitability. So that would usually entail fast synchronous interactions of the kind measured with EEG. So there's lots of biophysics and neurobiology about the physiology of gain control. That is the place that one encodes the precision, say, of prediction errors. On the point of view of machine learning, exactly the same mechanisms can be found in certain kinds of machine learning, not all of them, but I think the most compelling example would be the transformer architectures that are underneath the hood in ChatGPT and GTP4. And they actually have something called attention. And this attention basically allows them to pick up things that are predictable on the basis of stuff that's happened in the past, in this instance, in a stream of text, for example. So they are using exactly the same sort of modulatory biasing or gating, in this instance, in a very simple way, in the context of an autoregression-like model over time, that is being instantiated by the top-down control of the felt uncertainty that would be the ascending neuromodulated transmitter systems like dopamine. That has different roles depending upon where it projects. So when you talk about uncertainty generally or precision generally, you're talking about attributes of belief structures, Bayesian belief structures that are generally subpersonal, and therefore you have to also say precision of what. So the precision that, say, a mesocortical as opposed to a mesolimbic dopaminergic projection would control would be the precision of something that's very different depending upon what those beliefs were about.
In my own area of adolescent brain development, you see a reorganizational period of brain development around puberty, and especially the dopamine activity you're mentioning now. There's some evidence that sex hormones are involved in restructuring or modulating how dopamine is processed, and that leads to a whole bunch of changes in reward sensitivity and inhibitory control, and at a high level in impulsivity and risk-taking. I'm wondering how you would interpret all that from a perspective of active inference, because it seems like what's happening when you have a critical period of brain development, whether that's in early childhood or this second critical period of puberty, what's happening is that the meta parameters of this active inference process are being changed such that plasticity goes up. So you could be taking in the same amount of information, but during certain critical windows, you're more susceptible to changing your worldview more, or the internal model is influenced more by the same amount of information compared to later in adulthood when the brain is more static.
Yeah, no, I think that's absolutely right. And how would it be explained under active inference? In a relatively straightforward and possibly even easy to simulate way. So it sort of comes back to what we were talking about before about the coupling between different scales of the same kind of process. So we're talking here about a particular developmental phase, and it's a developmental phase that is associated with all sorts of requirements for new learning, either in terms of discovering your adulthood or preparing to leave home to go to university or to your first job, or from an anatomical perspective, a time of great pruning, say in the frontal radiations. So it's a restructuring of the brain. So you ask yourself then, well, how do I understand the coupling between the different levels of optimization of my fantastic model, my generative model? Well, we said earlier that sort of you've got to have the right kind of learning in terms of experience-dependent plasticity to enable you to do the structural learning, to prune or remove redundant connections, say in the elimination of redundant white matter connections in the frontal lobe, that is characteristic of late adolescence, for example, making the brain more efficient. And of course, you have to have the right pruning in order to retain the right synapses to do the experience-dependent learning. So what does that mean? Well, it just basically means that if you are going to engage in some structural learning and remodeling, then you need to emphasize the epistemic aspects of your and behavior. So you become more information seeking. So remember before that the plans that we commit to, including adolescence, can be described as if they are in the same instance maximizing expected information gain and maximizing expected, say, value, where value is the log of your preferred states of being. But those do depend upon the precision of your beliefs about your preferred outcomes. So in the absence of any preferred preferences, if you feel very adventurous and you don't care what happens to you, which is a certain characterization of certain children or certain points in life, then what you are just left with is the epistemic gain. So what you'd predict would be that if there's a scheduled series of developmental stages of that are all driven by the selection of the good models that have the right degree of coarse graining, which usually entails minimizing complexity by removing degrees of freedom. So good models usually, as they get older, get simpler and smaller. And certainly, there's an argument to suggest that normal aging, you see that decline in, say, synaptic density, and certainly in white matter connections. But that's particularly accelerated, during adolescence. You would argue that you do indeed want to engage more in sensation-seeking, novelty-seeking, exploratory behavior, which is exactly what you would get if you had if you increased the expected information gain contribution to what underwrites your plans and provides an overall tone to the kind of behaviors that I engage with. And interestingly, it's interesting you asked that question, because if you look at the maths of the things that control the relative contribution of my epistemic habits relative to those based upon the expected information gain, the quantity that seems to provide the balance looks or behaves in exactly the same way that dopamine behaves. So it may well be that dopamine has a very special role, say possibly certain projections of the dopamine system may have exactly this role in setting the temperature of, or the gain of, certain imperatives for plans relative to habitual plans, or the way that I normally do things. And looked at like that, it does not surprise me to hear that dopamine plays a particularly important role and anything that acts as a neuromodulator or affects neuroplasticity, including things like steroids and sex hormones and like, will play a very important role in optimizing the degree of epistemic behavior, explorative behavior relative to exploitative behavior of the kind that would be driven by your prior preferences. So you could, in principle, simulate this, and it would be entirely Bayes optimal. It does require, though, to specify the scheduling, if you like, the curriculum learning, the epigenetic programs of neurodevelopment. But if you specify those as contextualizing certain levels of certain degrees of learning to learn, then I'm sure you could simulate that, in a biologically very plausible way.
So there's meta optimization in the sense of not only learning to learn now, and not only learning to learn across time, but learning to learn itself and modifying the weights at which you take in new information and update your beliefs.
Absolutely, yeah. And just to sort of really join all those dots, the precision is almost universally a learning rate. So if you just think about the basic mechanics of belief updating, whether you're thinking about a predictive coding scheme, a Kalman filter if you're an engineer, if you do behavioral psychology, a Rescorla-Wagner model, you're changing your beliefs, whether these are beliefs about sort of connections or beliefs in perceptual inference, you're changing your expectations about the world in proportion to a prediction error. It could be a reward prediction error in say Rescorla-Wagner models, and the rate at which it changes is the precision you afford that prediction error. So it's usually sort of alpha in a Rescorla-Wagner model. That is the precision you're affording the prediction error. So that's why I was emphasizing precision weighted prediction errors before. But when you look at the form of the equation, the rate of change in my expectation is equal to precision times prediction error. And as you increase the precision, you increase the learning rate, literally. So I think it's a really nice sort of juxtaposition the way you ask the question, that there is an optimal way to learn, and that's just optimizing your learning rates. That just is getting the precision right, which is just another facet of quantifying your uncertainty. So when I've got very precise information, or there's lots of epistemically rich information that I'm actively harvesting because I'm going to discos and doing bungee jumping and exploring relationships as an adolescent, then this is very precise information I've actively garnered, and I'm going to afford it then a greater learning rate simply by precision weighting all of the ensuing prediction errors that are driving my experience-dependent plasticity.
Not only will I be spending another several years thinking about this, but doing so while my brain is in the last few years of maturation. We've covered a lot of material today, Dr. Friston. Thank you very much for your time.
My pleasure. I've greatly enjoyed talking to you. Thank you.